Hello everyone, I'm Norman Wahlberger and welcome to Algebraic Calculus. In this video we're going to start looking at tangents, which is traditionally part of differential geometry, but we just need enough about that story to make some nice calculations in the integral calculus side of things. So the tangent line story is one also that has a long history, but it's not really quite as deep a history as the integral calculus. So here's the basic story. We have a curve and we have a point on the curve, and we're interested in getting a hold of this line, this tangent line, to the curve at the point which best approximates the curve near that point. All right, so that's a kind of a geometrical definition. The tangent line to a curve at a point meets the curve only once near A and approximates the curve there. So if we magnified the region around there, then the curve and the tangent line would look pretty close. Okay, this is rather an informal definition, so we just should take this as an initial orientation. But nevertheless, this problem of finding tangents to curves became a very big topic in the 17th century. People were actually interested in calculating or constructing tangents to curves. So quite a few illustrious people studied this problem, including Fermat and Descartes, Roberval, Hud, Sluis. They all developed techniques for computing or calculating tangents. Descartes said that this was the most useful and general problem that I know in the context of geometry. And Fermat put that to use in the very explicit problem of finding maxima and minima of functions. Or actually, perhaps local maximum and local minimum might be a little bit more accurate. So here we have what we informally might call a function, traditionally y equals f of x. And we see that at this point here, at the point x1, it's reaching a local maximum. It's bigger at x1 than it is at nearby points. And here at x2 we have a local minimum, and over here at x3 we have another local maximum. And Fermat realized that we could find those local maxima and minima by essentially having control over tangent lines, because at those points the tangent lines are going to be horizontal. It's a key insight of Fermat. So we can find these points by finding out when the tangent lines are horizontal. But the problem of finding tangents actually goes back to the ancient Greeks. In particular, Apollonius was well aware of the importance of tangents to a conic. And he was, in fact, in possession of constructions of tangents. And one particularly interesting approach is through this idea of polarity, that to a conic we can actually associate a correspondence between points and lines in such a way that the point approaching the curve means that the line approaches the tangent to the curve at that point. So this polarity, I want to give you a very quick sort of idea of how it goes. We're not going to go into details. I just want you to see how it could be used to solve this problem of actually constructing a tangent. Suppose we're given a conic like this, and we actually need to make a very exact construction of the tangent at that particular point A. How are we going to do that? So let me illustrate something. Let's see if I can make it work. So let's choose a point somewhere here, and I'm going to construct the polar of this point, which is a line somewhere. It'll be somewhere out here somewhere. And how I'm going to do that, and this was known to Apollonius, I'm going to choose two lines that pass through this point, and hopefully I can do this in a way that's not going to be too difficult. So these two lines determine 4 points on our conic, and the 4 points have some auxiliary lines that we can draw. That one and that one. They're kind of opposite things, and they will meet at another diagonal point, if we like. Maybe I'll put it in a square. And then there's another 2 set of lines, of opposite lines. That one there, and this one there. Okay, and they will meet at that point there. So having done that, then we can, and I might use a different color, then we can construct the line through these 2 diagonal points that we've just made, and that turns out to be the polar of the original point that we started. I might call color that one red. Okay, so that the dual or the polar of this point is that line. And remarkably, as Apollonius realized, this is independent of the actual lines that we chose through the point to make the construction. Very beautiful fact of projective geometry. Okay, so how can we use this? Well, let's do the same kind of thing again, but I'm just going to first draw a line, maybe in green, through our point A that we're actually interested in and the point that we've just been analyzing. Okay. And let's choose another point on that line. Let's say this point here, and do a similar kind of story to find the polar of this point. Okay. So I'm going to do the same kind of thing. I'm going to choose two lines that go through here. Maybe I'll use dotted lines. Okay. And maybe, so we're going to get these 4 points. Where's the other one? Over here. And now I have to find the other two diagonal points of this quadrilateral. So I have to join these up. So if I join those ones up, I get another line sort of like this. And if I join the other two up in this direction, I will get a line that looks sort of like this. And they're going to meet down here in the corner somewhere. Okay, and we'll make a square around there. And then we're still talking about these sort of dotted quadrilateral points. There's still another set of lines that are formed by those 4 points. There's this line here and this one here. Okay, so we get another diagonal point. And then if we connect these two, we're going to get the pole of this one here. So maybe if I color this one green this time, and I will draw the dual roughly to go in this direction here. Okay, so I'm going roughly like this, something like that. Okay, so this point here has its dual here. This point here, the green one, has its dual here. Dual, I call, that's the polarity correspondence of Apollonius. And that has the interesting consequence that this intersection point, is going to be, and I'm going to also color it green, that's going to be the dual of the line joining the red one and the green one. It's a very beautiful story, this polarity business. So if we did the same thing with this point here and drew two lines and did diagonal points, we would find that the line that we get was the original green one. Okay, now because this point A lies on this line here, it turns out that the dual of A will pass through this polar point. So in other words, the tangent to the point A, or at the point A of the conic, can be obtained now by joining A to this point that we found. And even though I've only done it sort of roughly, and this is actually not a conic, it's just freehand drawn, you can see that still this is a reasonable estimate to what might be the tangent to the conic at that point A. So this is a purely projective construction. Let me label it. So there's the tangent to the curve C at the point A. And it's a purely projective construction that Apollonius would have been familiar with. In the 17th century, a remarkable theorem was discovered by Blaise Pascal when he was a teenager that transformed the theory of conics and allowed an alternate, perhaps simplified way of finding tangents to conics be understood. So here is just an overview of that. So here's Pascal's theorem. It relates 6 points on a conic, and it's a generalization of famous Pappus's theorem for 6 points formed by 3 points on 2 lines. So here's a conic, points A, B, C, and other points A prime, B prime, C prime, and then we create these auxiliary points that are meets. So if we join A to B prime and A prime to B, they meet at the point C double prime. If we join, say, the B's and C's, B, C prime with B prime, C, then those lines meet at a new point, we'll call it A double prime. And finally, if we join the A's and the C's, A, C prime and A prime, C, those two lines meet at a new point, B double prime. And there they are written out in terms of products. So A double prime is the meet of this line with this line. Okay, and the theorem is that these 3 points that we so construct, A double prime, B double prime, and C double prime, are always collinear. Very beautiful, beautiful fact of conics, and actually very powerful fact. And in particular, it was sort of then realized that this theorem, when we extend it or sort of look at the special degenerate case when 2 of the points coincide, actually yields tangents. So without going into a lot of details, we'll talk about it in the worked problems, but what happens, let's say, if we look at the point A and C prime, if we apply this theorem to the case when A equals C prime. So you can imagine, say, moving C prime around until it gets pretty close to A. What's going to happen? Well, this line AC prime that joins A and C prime, well, that's going to move towards being a tangent. So we can kind of think of the tangent being the line AC prime here in the special case when A equals C prime. Okay, so imagine if we sort of rubbed C prime out and replaced A with C prime, so A and C prime are the same. Then what's going to happen is that since we can get at C double prime and A double prime independent of this line here, we're going to be able to find this red line. And if we believe Pascal's theorem, then this point B double prime given by this combination should also lie on that line. So that means that this point B double prime can be found by taking the line here and meeting it with A prime C, which are still a legitimate chord. So once we have B double prime, then we have a point on this imaginary kind of chord, A, C prime, and we can just connect A with B double prime, and we're going to get this tangent. So the picture would not look like this, it would look different, but the B double prime construction would end up being B down here somewhere, or somewhere on this line that would allow us to draw this tangent. So that's a very quick derivation. For the details, you could look at the worked problems. But the point is more or less that finding or constructing tangents, and maybe even defining tangents, was a highly non-trivial thing for 17th century mathematicians, and even earlier mathematicians. They realized that you can't just say, here's a curve and here's a point, and consider the tangent. Right? What does that mean? You have to construct the tangent before you can talk about it. That's a very important principle. And here we see that this problem is geometrically non-trivial. It requires some deep understanding of the underlying geometry of the curve that we're talking about. So in this video, we're going to look at an alternate technology, which is algebraic, an algebraic way of dealing with this same geometrical problem, illustrating the power of algebraic thinking to solve or help us understand geometrical situations. Now, in classical courses of calculus, tangent lines are often defined and computed as limits of chords or secants. So here's a curve again, and let's say we're interested in tangent at the point A. Then what we might do is consider first a secant or a chord that joins A with some other point on the curve, in this case B. That's a secant or a chord. And then the idea is, well, let's let B move towards A. And as B moves towards A, this is fixed, then this secant line ought to move towards the tangent. And as B is very close to A, then A and B should determine a line which is pretty close to being a tangent. But it's a rather delicate thing, because as A and B get very close, then it's a sensitive thing drawing that tangent line. It's hard to do accurately. But nevertheless, theoretically, this is often the way things are approached, and it is an attractive way of thinking, for sure. And it's sort of what we were using a little bit in the Pascal argument as well. But nevertheless, unfortunately, the idea that the tangent line is some kind of limit of secant lines, we might use this notation limit as B approaches A of the secant line AB, that's somehow a definition of the tangent. That is problematic on logical grounds, because for typical curves, this requires an infinite amount of work. You can't actually get at this limit without actually going through an infinite amount of intermediate steps. So it's really the result of a process that you have to complete by going to infinity. And in this course, we don't want to do an infinite number of operations. So somehow we have to sidestep this approach and this orientation towards tangent lines. Okay, so that's a major challenge, and we do that by exploiting the algebraic setup in which we're working. And we're going to be looking at how we can do this kind of thing for curves which are parametrizable, algebraically parametrizable. We'll see that there we can employ some beautiful trick, really, to get at the tangent purely algebraically. Well, so to illustrate the idea, let's have a look at the example of the parabola and calculate chords and tangents to the parabola. So we're talking about y equals x squared with parametrization t and t squared. So here are 2 points on the parabola, A with coordinates t and t squared, and B with coordinates u and u squared. And we're going to assume that they are distinct points, okay? They're different, so t is different from u. And now the chord AB we can calculate by using the join of points formula. So we write down the projective coordinates for both A and B. So there's A in projective coordinates, and there's B in projective coordinates. And then we use this sort of cross product idea to take the cross product of these vectors to get the coordinates of the line joining them. So the first coordinate here is obtained from the second and third entries, tu squared minus t squared u. The second entry is obtained from the third and first entries, t squared times 1 minus 1 times u squared, so that's t squared minus u squared. And the third entry is given by the first 2 entries, 1 times u minus t times 1, so we get u minus t. Now pleasantly, there's a factor of u minus t in each of these expressions. So we factor the first one as u minus t times tu, the second one is t minus u times t plus u, and the third one is just u minus t. And now, remember we've said that u and t are distinct, so u minus t is non-zero. So we can cancel that common factor that's occurring in each of these terms. We get tu over here. Here we get a minus t plus u, and here we just get 1. So then this is the projective coordinate for the line or the chord AB. As an explicit equation, it has the form of tu, that's the constant term, minus t plus u x plus y equals 0. And if we want to rewrite that in a more familiar way, we could bring the y to one side, y equals t plus ux minus tu. That's quite an attractive, elegant formula for the chord, determined by 2 points on the parabola in terms of the parameters describing those 2 points. So here's a picture of the parabola y equals x squared. The axes are a little bit tilted. That doesn't bother us. There's some familiar points, including the point 2, 4, the point minus 1, 1. And we're interested in, say, in the chord between these 2 points. That's the case when t equals 2 and u equals minus 1. There's the formula for the chord from the previous slide. And if we set t equals 2 and u equals minus 1, this becomes a 1. And this number here becomes minus 2. So altogether we get y equals x plus 2. And that is indeed, you can check, the equation of the line that passes through these 2 points. Y is x plus 2. Y is x plus 2. Easy. Now, how do we get at a tangent? Suppose that we're interested in the tangent to this curve at the point 2, 4. In other words, when t equals 2. We're going to perform a very simple-minded kind of trick, I suppose. What we're going to do is we're going to take the equation for the chord and just set the second parameter, u, equal to the t that we're interested in. We only have 1 point now, t equals 2, and we just take this equation and set u equals t in it. So if u equals t, then we get 2t here, so we get 2tx. And if t equals u, then we get minus t squared. So this is now an equation that does only have the parameter t in it, not t and u. And the claim is that this is the equation of the tangent at the point parameterized by t. Now you might say, well, isn't this sort of like a limit? Like what we're really doing is we're letting u approach t. And you can think about it that way. You can think about it, certainly, that we're thinking about the u as varying, and the varying could, proceed, and u's getting closer and closer to t. And in the limit, sort of u equals t. But notice that actually what we're prescribing here does not involve any limiting process. We're just saying, take the equation of the chord and set u equal to t. Replace u with t. Completely finite algebraic manipulation that doesn't necessarily need to be connected with any kind of infinite process that we may have in our mind. Okay, we may have some interpretation, but we don't need to have the algebra reflect that. The algebra is just cut and dried. In particular, when t equals 2, this becomes y equals 4x minus 4, and you can check that that's a reasonable equation for a tangent. It's a line with y-intercept minus 4, so it goes through this point here. Its slope is 4. That's usually sort of associated with the derivative of the function and so on. But notice that we're not relying on any prior theory of derivatives here. Okay, we haven't gotten there yet. Okay, this is just pure algebra, just exploiting what we know about joins of points and then setting u equal to t. Okay, and we get more than the derivative, even if you know what that means. We're getting really the tangent line itself, and it's the tangent line which is really the crucial object, not its slope. Slope is interesting, but so are a lot of things. So is the y-intercept or the x-intercept or whatever else we might be interested in. But it's the equation of the tangent itself which is of primary interest. All right, so now here is the strategy. The strategy for finding a tangent to a parametrized curve gamma. There's the curve gamma. We're assuming it's parametrized at a point A corresponding to a parameter value t. And we would like to get at this tangent line. First of all, define what it is and compute it. And here's our strategy. First, find the equation of the chord for general parameters t and u. T, u, general parameters. Find the equation of the chord joining those 2 points on the curve. So now what we do is we cancel factors of t minus u. We have some expression for the chord, and that expression will typically be factorizable in terms of t minus u, because when t equals u, then the whole process of finding a chord between 2 points breaks down. So if you think about the process of taking the product of a projective point with another projective point, these sort of a, b minus c, d terms that we get in the product, each of those is going to be 0 if the 2 points are actually the same. And that's telling us that t minus u is going to be a factor. So we can cancel those t minus u factors. There is a perhaps small but non-zero probability that there might actually be t minus u factors to some higher power, like maybe t minus u squared is in each one of those 3 expressions, in which case we should cancel all of them. Okay, so cancel as many t minus u's as we can. After we've done that, then we set u equal to t. So up to this stage here, we were assuming that u and t were different. But once we have the equation of the chord, then we can remove the common factor t minus u, and then we can replace the u with t. And we get an equation for the tangent line to the curve at the point A, parameterized by t. And it's a completely algebraic process. And it's a lot of fun. Right? So we can take algebraically parameterized curves, and we can play this game, and you can see that it works, and it works beautifully, and we get equations for tangents. So this is a very hands-on technology that you can apply to a wide variety of curves as long as they're parameterizable. Okay, and it's a great exercise to do this, to tackle this issue for a lot of famous curves. For the parabola y equals x squared, we've already seen its parametrization. Everything projectively is 1t squared, so there's the x and the y coordinates. And then the equation of the tangent line to the parabola at that point is t squared to minus 2t to 1. Similarly, we can try y equals x cubed. There's its parametrization, and there's its tangent at that point. Y equals 1 over x, well, the standard parametrization for that would be x equals t and y equals 1 over t. So you might expect that we should write 1 t and 1 over t. That's fair enough, but we'd like to get rid of denominators, and the projective form of our coordinates is ideally suited for that. So we can multiply through by that t in the denominator and getting t squared to 1. And the tangent to that is minus 2t to 1 to t squared. Here then are the unit circle and the relativistic hyperbola. They are very parallel, their equations are quite similar, their parametrizations are quite similar. So here's the standard rational parametrization of the circle expressed in projective coordinates. Here's the standard parametrization for the hyperbola expressed in projective coordinates. And then here are the corresponding formulas for the tangents. Note pleasantly that these tangent formulas look a lot like the actual projective formulas themselves. It's quite pleasant, and there's a nice parallel between them. So the tangent to the unit circle is 1 plus t squared to minus 1 plus t squared to minus 2t, while the tangent to the relativistic hyperbola is minus 1 plus t squared to 1 plus t squared to minus 2t. And finally, the semicubical parabola, y squared equals x cubed, which is quite an interesting curve. It has this parametrization. X is t squared and y is t cubed. And then in terms of that parametrization, you can calculate that the tangent line has projective coordinates t to the fourth minus 3t squared and 2t. Now there's something a little bit interesting and subtle that happens with this one. You might think, well, wait a minute, there's a common factor of t here, why don't we cancel that? Well, you can cancel that common factor as long as t is not equal to 0. But actually t equals 0 is a legitimate point on this curve. However, when you look at t equals 0, the form for the tangent becomes 0 to 0 to 0, which is not a valid proportion, telling us that something has gone wrong at the point 0 with this computation. There's something fishy about the tangent to this curve at that point. So the algebra is telling this to us already. Okay, so it's a great exercise to work through these examples, and in the course proper, there'll be plenty of opportunities for you to practice and see this in action. So very important technology. 17th century mathematicians would have liked this very much. There's much to learn. I'm Norman Wildberger. Thanks for listening.